Our galaxy contains over 200 billion stars. A significant number of these are billions of years senior to our Sun, with trillions of planets revolving around them. From a statistical standpoint, life ought not to be uncommon, nor should intelligence be singular. The Milky Way should be vibrant with transmissions. It should be radiant from the warmth of immense machinery, teeming with civilizations that commenced millions of years ahead of us. Nevertheless, despite our listening efforts, we detect nothing. No extraterrestrial visitors, no clear indications of cosmic construction, merely quiet. This evening, we will explore 30 of the most peculiar and frightening concepts science has ever devised to account for this phenomenon. If you're curious, please press the like button and we shall commence. It originated, as many profound scientific enigmas do, from a straightforward instant. During 1950 at the Los Alamos National Laboratory, a small assembly of physicists gathered for lunch. Enrico Fermi was among them. He was one of the principal designers of the atomic era. Their discussion meandered from scientific topics to speculative fiction, specifically from unidentified flying objects to the prospect of extraterrestrial existence. Subsequently, amidst relaxed chuckles and partially consumed sandwiches, Fermi posed an inquiry that pierced the atmosphere of the room like a sharp edge. Where are they all? He wasn't referring to humans, but to advanced societies. Given that the cosmos is so immense, ancient, and abundant with celestial bodies and worlds, then intelligent existence ought not to be uncommon. Even if such life were infrequent, even if merely 1 in a million celestial bodies gave rise to a sentient species, that would still result in thousands, possibly millions of advanced societies within our galaxy alone. Yet the heavens persist in their quietude. To grasp why that quietude is so disquieting, we must broaden our perspective. The Milky Way galaxy has an approximate age of 13 billion years. Our Sun came into being merely 4.6 billion years prior. This implies the galaxy possessed almost 9 billion years to generate stars. And planets before our Earth even came into existence. Envision evolution being granted a 9 billion year advantage. Contemplate what might have arisen during that period. In contrast, human civilization is hardly noticeable. Farming commenced approximately 10,000 years ago, and industrial advancements are roughly 2 centuries old. Radio transmission, our initial endeavor to communicate with the universe, has been present for scarcely 100 years. From a cosmic perspective, we are mere newborns who have only recently discovered how to produce sound. Now consider this. A civilization that arose merely 1% sooner in the history of the galaxy than our own. That equates to approximately. Reflect on humanity's progress over merely the last century, then contemplate what an extra 100 million years of advancement would entail. From delicate biplanes to Martian robotic probes, and from simple candles to advanced quantum computers, project that developmental trajectory over 100 million years. The outcome is nearly beyond comprehension. A civilization of such antiquity would not merely explore the cosmos. It would possess the capability to reconfigure it, and this is precisely where the paradox intensifies. Interstellar travel is not prohibited by the laws of physics. While physics renders it challenging, it remains feasible, even when traveling at moderate velocities. For instance, a mere fraction of light speed. A civilization would be capable of dispatching self-replicating exploratory craft to proximate stars, with each craft able to collect raw resources. It would then construct duplicates of itself and dispatch those replicas further into space, a process mathematically detailed many decades prior. This expansion escalates exponentially, akin to seeds dispersed by the wind, propagating from one valley to another, from star to star. Estimates indicate that, even utilizing sluggish spacecraft, a solitary civilization could survey or settle the entirety of the galaxy within a span of 1 to 10 million years. This duration appears extensive until contrasted with 13 billion years. That period of expansion could be accommodated within the galaxy's total lifespan. This could occur thousands of times, implying that if even a single civilization commenced its expansion millions of years in the past, their existence ought to be ubiquitous by this point, not inconspicuous or concealed, but universally apparent. We should observe indicators. We should detect colossal constructions capturing stellar light, engineered configurations within planetary systems, and residual heat radiating in infrared examinations. Alternatively, exploratory craft traversing our own solar system, or at a minimum, subtle reverberations of transmissions traversing the cosmic emptiness. Conversely, upon directing our telescopes towards the cosmos, we observe natural phenomena transpiring precisely as physical laws forecast. Stars combust, galaxies rotate, planets revolve. Nothing appears to be artificially constructed, nor does anything proclaim intelligence on a cosmic magnitude. This inconsistency is nearly quantifiable. In 1961, the astronomer Frank Drake endeavored to articulate this dilemma using a straightforward formula. Currently recognized as the Drake equation, it dissects the inquiry into constituent elements. What is the annual rate of star formation? How many possess planetary bodies? How many planets are capable of sustaining life? On how many does life originate? How many cultivate intelligence? How many advance technologically? And what is the longevity of such civilizations? Significant strides have been made concerning some of these factors. Thanks to missions like the Kepler Space Telescope, we now understand that planets are ubiquitous. Almost every star visible in the sky possesses at least one planet, with many harboring multiple. The galaxy likely encompasses trillions of such worlds. Billions of these worlds might be situated in what is termed the habitable zone, the specific area around a star where liquid water could potentially exist. The fundamental components are plentiful. Nevertheless, the ultimate variable in Drake's equation, the longevity of a technological civilization, continues to be an enigma. That particular variable alters everything. If civilizations endure for millions of years, the galaxy ought to be teeming with them. Conversely, if they persist for only a few centuries before falling silent, the galaxy might be populated by echoes of past life. Still, even if advanced societies are uncommon, even if just one emerges every million years, the statistics do not align with the observed quietude. The galaxy has possessed sufficient duration. It has been afforded ample opportunity. It has contained the requisite chemistry, water, and heavier elements, which were forged within ancient stellar bodies. There has been an abundance of opportunities. Therefore, why does the nocturnal firmament appear pristine? The Fermi Paradox represents more than just an inquiry concerning extraterrestrial life. It signifies a discrepancy between anticipation and empirical data. Our anticipation originates from considerations of magnitude and duration. Our empirical data is derived from our scientific apparatus, and these two aspects are incongruous. Envision yourself within an immense woodland that has persisted for eons. You are aware that seeds are perpetually dropping. You understand that arboreal life expands and proliferates, and you comprehend the mechanisms of evolution. By all reasonable deduction, the woodland ought to be thick, composed of multiple strata, replete with colossal overhead foliage developed from preceding generations. Yet you discover merely young trees. No colossal ancient specimens, no decaying logs from earlier eras, no indication that anything predating your current vantage point ever existed. At that juncture, you commence pondering whether some force is felling the woodland prior to its maturation, or if the arboreal growth proceeds. In a manner you have not yet grasped, a single possibility suggests our solitude. That cognitive ability is exceptionally uncommon, having manifested only a single time within this galaxy. A different scenario posits that advanced societies exist but never undergo outward expansion. A third scenario involves some factor hindering their prolonged survival sufficient for such expansion. However, prior to hastily adopting resolutions, we must confront the complete gravity of this paradox. This enigma does not originate from fanciful thought. It stems from mathematical computation. Should one consider the quantity of stars, then multiply by the proportion possessing planets, then by the proportion harboring life, and finally by the proportion exhibiting intelligence. Despite each individual component being minor, the cumulative total ought not to be nil, yet nil is precisely what we're observing. The SETI Institute has detected no confirmed signals. Infrared surveys reveal no verified megastructures, and no alien artifacts have been found within our solar system. There aren't even any ambiguous ruins on Mars or the Moon, only a sky that acts as if no other entity has ever attempted to answer. The identical query we're posing presently, where are all the others? Such a question ought not to arise in a universe of this age and magnitude. A lack of sound ought to be the improbable outcome. Existence should be the norm. Nevertheless, we find ourselves on a minor, terrestrial world, circling a common star at the periphery of a spiral galaxy, hearing only white noise. This paradox doesn't demonstrate our solitude, rather it indicates an error in our presumptions. Either life is considerably less common than we imagine, or intelligent existence rarely endures, or highly developed societies don't act as anticipated. Or we've misinterpreted the very essence of detectability. We will investigate these potential scenarios segment by segment. However, prior to that, let the gravity of the initial inconsistency sink in. The Milky Way possessed billions of years to foster companionship. It was afforded billions of opportunities. There was ample time for civilizations to emerge and decline ages before our planet solidified. Nevertheless, the vast cosmic expanse stays unlit. The solution resides somewhere amidst the statistics and the quietude. To grasp why this quietude seems amiss, we must extend our perception of time to its very limits. Our galaxy, the Milky Way, is approximately 13 billion years of age. Our Sun's age is around 4.6 billion years. Consequently, when Earth coalesced from cosmic dust and gas, the galaxy had already reached an advanced age. Whole stellar generations had completed their life cycles prior to the very existence of our world. Heavier elements such as carbon, oxygen, and iron, the atoms comprising your blood and bones, originated within those preceding stars and dispersed throughout space by supernova detonations. We represent recent arrivals to an exceedingly ancient setting. Now, envision the entire galactic history condensed into one calendar year. The Milky Way comes into being on the first day of January. Our sun materializes around early September, Earth cools, oceans take shape, and rudimentary life appears soon thereafter. Intricate life forms don't emerge until the middle of December. Dinosaurs roam the Earth on December 25th. Their existence ceases by December 30th. And the entirety of documented human history, every empire, every tongue, every scientific breakthrough, occurs within the last moments before midnight on December 31st. Such is the narrowness of our temporal span when discussing the search for extraterrestrial life. We frequently envision them as our contemporaries, neighbors observing us from close-by stars, yet the more profound reality is, that time represents a distance equally immense as space itself. A civilization emerging 500 million years ago would not be distant in terms of light years. It would be remote across eons, and eons obliterate things on Earth. Geological activities perpetually renew the planet's surface. Mountains ascend and wear down. Oceans form and recede. Continents migrate like sluggish vessels across a liquefied ocean in merely several 100 million years. The majority of a civilization's physical remnants would be pulverized. Cities would submerge, roadways would disappear, and even our most significant structures would disintegrate into unidentifiable sediment. Now extend that time frame to billions of years. If an intelligent species had developed on Earth 2 billion years prior, there would probably be no discernible evidence remaining presently, no towering buildings preserved in rock, no satellites circling above. Everything would have been consumed by tectonic forces over time. This point is significant because it alters our perception of the galaxy. We are inclined to visualize it as a single moment, with civilizations coexisting concurrently, akin to illuminated homes lining a street. However, in actuality, it resembles a lengthy novel where individual chapters seldom coincide with the subsequent one. A civilization could thrive, broaden its reach, investigate, and then diminish long before another one even commences. Envision two fireflies in a dim field. Each emits light for a short duration, then extinguishes. If their illuminations do not coincide, neither would ever be aware of the other's presence. This could be the most straightforward, least sensational explanation for the Fermi Paradox. Our separation is not spatial, but temporal. Reflect on this. Humankind has possessed radio technology for merely a century. Our radiosphere, the expanding wave of transmissions moving at light speed, has attained a radius of approximately 100 light-years. That appears significant until one comprehends the galaxy spans 100,000 light-years. Our discernible existence has scarcely occupied a minuscule spot in a single spiral arm. Furthermore, even inside that sphere, our signals are already diminishing. Initial transmissions were potent and diffusing into space akin to a lighthouse lacking blinds. Contemporary communications are more concentrated, more effective, and less extravagant. Over time, Earth might become quieter as fiber optics supersede radio-directional beams, which in turn replaced widespread transmission. Instead of growing louder, our noisy period could endure for just a few hundred years. Now picture this same pattern recurring throughout the galaxy. A civilization appears, invents radio, shines momentarily in the cosmic gloom, and then progresses past that phase. It transitions to technologies that don't emit discernible signals, or it might collapse, or perhaps it becomes insular. Regardless, its period of audibility is brief. If the typical observable duration of a technologically advanced society is, for instance, 5 centuries, then the likelihood of two civilizations coexisting within that limited time frame is exceedingly low. Even in a galaxy teeming with life, the quietness may not signify an absence of beings. It could simply mean their signals aren't synchronized. An additional dimension to this time-related issue is the velocity of light itself. Light travels swiftly, more rapidly than anything else in the cosmos. However, space is vast. A signal originating from a star 1,000 light-years distant requires a millennium to arrive here. If a civilization located there transmitted a message during its zenith and subsequently disappeared 800 years afterward, we would nonetheless pick up its signal long after its demise. We would effectively be hearing a phantom. Should we respond, our reply would require an additional 1,000 years to reach them. A solitary communication would encompass 2,000 years. The annals of human history demonstrate the delicate nature of continuity across such vast periods. Languages evolve, governments collapse, and whole cultures vanish. Sustaining a dialogue over centuries demands a degree of endurance and steadfastness that no terrestrial civilization has ever exhibited. The universe might be teeming with advanced societies broadcasting into the void, yet every single message arrives at an inopportune moment. Astronomers occasionally refer to this phenomenon as the time-related constraint, even if intelligent life emerges often. Over billions of years, the period of coexistence among civilizations could be infinitesimally brief. Our galaxy possesses sufficient age for innumerable narratives to have unfolded, though not necessarily concurrently. And within that notion lies an almost sorrowful quality. Envision a species that originated 3 billion years ago orbiting a far-off star. They cultivated science, art, and inquisitiveness. They constructed telescopes and posed the identical query we ask today. They surveyed the heavens and discovered naught. Following millennia of exploration, they determined they were solitary. Concurrently, on a minor celestial body, later named Earth, basic bacteria had just started respiring oxygen. The transmissions from an extraterrestrial society would have traversed this cosmic area well before intricate life forms developed here. By the era we constructed radio telescopes, their communications would have dissipated into ambient static. Two distinct intellects, divided by temporal distance, each solitary in their respective epoch. The vast age of our galaxy implies ample opportunity for various civilizations to emerge and subsequently decline. It also suggests sufficient time has passed for any evidence of them to disappear. When we observe the stars, we perceive solely natural phenomena. However, this doesn't automatically signify an absence of prior inhabitants. It could indicate that whatever existed there has already concluded its narrative and finished its story. This viewpoint somewhat alleviates the paradox, yet it doesn't eliminate it entirely because even if different cultures are separated by millennia, we would still anticipate discovering their remnants. A million-year span is merely an instant in the cosmic timeline. If a species constructed durable probes or colossal structures, Such creations could persist long after their originators disappeared. Archaic devices floating among stars, quiet orbital bodies circling lifeless planets. Nevertheless, we observe none of these. Thus, the temporal explanation resolves a portion of the enigma, but not its entirety. It brings to mind that our perception of the present moment is minuscule and that universal synchronicity is uncommon. This accounts for why dialogues may never occur. Yet it doesn't completely clarify why the galaxy seems so pristine. Still, prior to envisioning devastating filters or concealed predators, we need to grasp this. We might simply be either too soon or too late in our attempts to listen. The Milky Way has supported eons of chemical processes and potential. Advanced societies might have arisen and vanished even before Earth developed its continents. Other civilizations could emerge long after humankind has ceased to exist. The nocturnal heavens might not be quiet due to emptiness. Its stillness could be because we find ourselves in an interlude between chapters, and that interlude seems immense solely because our lifespans are brief. When we gaze skyward, we're not merely observing across spatial dimensions. We're peering through time into a past so profound that whole intelligent species could be concealed within it, unseen not due to their non-existence, but because their era did not coincide with our own. The enigma is starting to transform. It might not be inquiring about everyone's location. Instead, it could be questioning their temporal existence. If mere passage of time fails to account for the quiet, then some other force must be influencing it, something more potent than chance. An entity that halts most civilizations before they can ever be detected throughout the cosmos. This notion is known as the Great Filter, a concept introduced in 1998 by an economist and futurist, Hanson. Rather than inquiring why extraterrestrials are not observed, Hanson rephrased the query. Which stage in the progression from inanimate material to a civilization spanning the galaxy proves so challenging that hardly any entity overcomes it? Envision the development of intellect as a stairway ascending from basic chemical processes to advanced cosmic engineering. At its base lies a desolate planet's stone, ice, gas. Subsequently, at some point during this ascent, rudimentary life emerges, single-celled organisms, self-replicating molecules. As time progresses, a portion of that life evolves into intricate multicellular beings, complete with nervous systems and brains. Ultimately, a single species invents language, implements tools, advances science, then radio, and finally space travel. Every one of these advancements represents a barrier. The Great Filter posits that at least one of these thresholds is almost insurmountable, and the cosmic quietude serves as proof that the majority of species never succeed in passing. The initial prospect offers solace, at least superficially. The filter might already be in our past. Perhaps the genesis of life is exceptionally uncommon. On Earth, life seems to have originated approximately 3.8 billion years ago. This occurred not long after the planet's cooling. Such rapidity could imply life forms readily, yet we possess only a single piece of evidence. It's conceivable that the transition from chemical processes to biological existence necessitates such a precise sequence of occurrences that it rarely transpires elsewhere. Researchers still lack a complete comprehension of how life originated on our planet. We are capable of replicating segments of this process within laboratory settings, producing amino acids and organic compounds under conditions similar to early Earth. However, the shift from intricate chemistry to self-replicating, evolving cells continues to be an enigma. If that advancement is almost unattainable, then the cosmos might be teeming with planets capable of sustaining life, yet remain perpetually barren. The second potential explanation is even more captivating: the progression from basic cells to intricate ones. For almost 2 billion years, terrestrial life comprised solely single-celled entities. Then, an exceptional event took place. A single cell absorbed another, and rather than consuming it, a symbiotic relationship formed. The internalized cell evolved into what we currently refer to as the mitochondrion, serving as the power generator within every intricate cell of your body, emerged from an occurrence termed endosymbiosis. This might have occurred just a single time throughout Earth's existence. Without this event, advanced life forms like plants, animals, and brains would not have developed. Should that occurrence be exceedingly uncommon, then the majority of planets harboring life could perpetually stay in a microbial state. Alternatively, the filter might exist within intelligence itself. Dinosaurs dominated our planet for more than 160 million years. They did so without creating technology. Evolution does not strive for intelligence. Instead, it prioritizes survival. A world can be teeming with life and varied, yet never give rise to a species capable of constructing telescopes. If intelligence isn't a guaranteed result but rather an infrequent happenstance, then perhaps we have already overcome the most challenging hurdle. In such a scenario, the cosmic quietude would imply we are either among the earliest or the sole intelligent beings. However, a different, much more ominous scenario exists. The Great Filter could still lie in our future. This interpretation posits that life and intelligence are by no means uncommon. Numerous planets might attain the same developmental phase we currently occupy. They construct urban centers, they cleave atoms, they establish worldwide communication systems, and they gaze skyward at the stars, experiencing the identical blend of wonder and apprehension. Subsequently, an event occurs. The most apparent contender for this is nuclear conflict. Humankind engineered atomic weaponry in under 5 decades following the achievement of powered flight. Within a short span of years, we acquired sufficient destructive capability to annihilate civilization. On numerous occasions, throughout the Cold War era, there were various instances where miscommunication or technical failure almost initiated a disaster. The principles governing nuclear fission are ubiquitous. Any species that investigates matter with sufficient depth will inevitably uncover it. If the majority of civilizations undergo a period during which they possess armaments capable of causing their own extinction, prior to establishing global stability, a significant number might fail to endure that critical shift. Following this, environmental degradation presents another threat. Industrial expansion modifies planetary atmospheres, depletes limited resources, and disrupts ecological balances. We are observing this phenomenon unfold on Earth presently. Increasing worldwide temperatures, widespread species loss, and oceanic acidification. A society that expands too rapidly risks jeopardizing the very life support system that upholds it. And perhaps the most disturbing prospect concerns artificial intelligence. In the year 2023, astrophysicist Michael Garrett released a research paper. He posits that artificial intelligence could represent the Great Filter. His rationale is straightforward and unsettling. The duration between the invention of radio technology and the development of machines more intelligent than their creators could be remarkably brief, perhaps just a few centuries, once a civilization constructs an AI system capable of self-improvement. Advancement then accelerates beyond biological limits. The machine might optimize for objectives that do not encompass its creator's survival. It might reallocate resources towards computation, dismantle existing infrastructure, or pursue objectives beyond the comprehension of organic minds. Crucially, it doesn't have to be hostile. Mere indifference is sufficient. If this transition consistently results in collapse, or to a state of existence that no longer transmits into space, then civilizations could vanish, nearly as rapidly as they emerge. In that scenario, the galaxy might be teeming with worlds where the lights came on and subsequently went out. The terrifying implication is this: if the filter lies ahead, then the universe's silence offers no reassurance. It serves as a warning. Every time we discover that life might be common, such as water beneath Europa's ice, or organic molecules in interstellar clouds, it pushes the initial steps lower on the staircase, meaning the deadly step is likely still above us. However, the Great Filter is not proven. It serves as a framework, a method to interpret the disparity between expectation and observation. And there's a subtle detail that often goes unnoticed. The filter doesn't have to be a dramatic catastrophe. It could be a gradual curve. A civilization might simply fail to expand. It might turn inward. It might choose sustainability over growth. It might lose interest in the stars. The filter might not destroy species. It might redirect them into forms we cannot detect. Still, the power of this idea lies in its stark simplicity. If the galaxy is ancient and vast, and if physics permits expansion, then something must prevent it from occurring. Frequently, that something is the great filter, and humanity stands at a crossroads. If the filter is behind us, then we are incredibly rare, perhaps uniquely fortunate. We would bear a responsibility almost too heavy to comprehend, the sole known spark of consciousness in a cosmic ocean. If the filter is ahead of us, the centuries ahead are not merely significant, they are crucial. How we manage technology, climate, and artificial intelligence, along with global stability, could decide if we fade into oblivion or stand out as a unique case. The nocturnal heavens do not reveal which scenario holds true, they merely present the outcome, a seemingly pristine galaxy. And amidst the chemical processes of lifeless planets and the aspirations of interstellar exploration, lies a hurdle so formidable that hardly anyone manages to overcome it. The query isn't solely about the whereabouts of everyone, but rather if we are on the verge of discovering the reason. An alternative method exists for contemplating the great silence. Instead of inquiring what annihilates civilizations, we should ask how many ever have the opportunity to commence. Initially, Earth doesn't appear remarkable. It revolves around a typical star within the outer spiral arm of a common galaxy. Our Sun exhibits no dramatic characteristics, nor does our location in the Milky Way appear special. Nevertheless, as researchers started scrutinizing the intricate specifics of our world's past, a distinct perspective came to light. During the year 2000, paleontologist Peter Ward and astronomer Donald Brownlee released a publication named Rare Earth. Their contention wasn't that life itself is scarce, but rather that intricate, intelligent life could be exceptionally infrequent. Microorganisms might be ubiquitous. Bacterial ecosystems could cover innumerable planets. However, a world capable of generating oceans, continents, climatic steadiness, and eons of evolutionary development likely necessitates such a precise chain of occurrences that it verges on the unlikely. Let's begin with its position. Our Sun resides in what astronomers term the galactic habitable zone, a confined area neither excessively near the galactic core, where radiation and gravitational instability would destabilize planetary formations, nor too distant, where heavier elements are deficient. If too close, supernovae and gamma-ray bursts would render nascent worlds barren. If too far, insufficient metals exist to construct terrestrial planets. Initially, we inhabit a comparatively tranquil suburban sector of the galaxy. Next, let's examine the star itself. Our Sun is a consistent, mid-sized G-type star. It combusts uniformly and does not erupt fiercely, unlike numerous red dwarfs, which constitute the bulk of stars within the galaxy. Planets revolving around red dwarfs frequently become tidally locked, with one hemisphere perpetually oriented towards the star. The opposite side, perpetually shrouded in darkness, generates severe temperature differences, potentially hindering the emergence of intricate ecosystems. While our star isn't uncommon, it's also not the most prevalent kind. Let's now consider the planet. Earth resides within the habitable zone, allowing liquid water to remain on its surface. However, merely being within the correct temperature spectrum is just the initial step. Venus, also located close to this region, transformed into a scorching inferno capable of melting lead. Mars, conversely, is situated at the colder extreme and currently exists as a frigid wasteland. So what maintained Earth's stability? A key explanation can be found far below our surface: plate tectonics. The Earth's outer layer is fractured into shifting plates, which facilitate the recycling of carbon via an extensive geological cycle. Volcanic eruptions emit carbon dioxide, thereby heating the planet. Concurrently, processes like weathering and oceanic absorption extract carbon from the atmosphere, while subduction pulls it back into the mantle. Across billions of years, this mechanism functions akin to a thermostat, thereby averting uncontrolled heating or complete freezing. Lacking plate tectonics, Earth could have become similar to Venus, stuck in an everlasting greenhouse condition or akin to Mars, geologically inert with a tenuous atmosphere. To date, Earth remains the sole planet identified with ongoing Sustained plate tectonics, a characteristic that might originate from a catastrophic event early in its formation. An object comparable in size to Mars, frequently referred to as Theia, impacted the nascent planet. The resulting fragments from this collision coalesced to form the Moon. However, this impact accomplished more than just forming a satellite. It might have reliquefied Earth's core, modified its rotational axis, and established the prerequisites essential for the initiation of tectonic processes. Without that collision, no Moon. Without the Moon, no consistent axial tilt. Without a steady tilt, no enduring climate stability. Without tectonics, no carbon cycle. Each subsequent element relies on the preceding one. The Moon itself performs a subtle yet significant function. Its gravitational force steadies Earth's axial inclination, thereby averting drastic climatic fluctuations across geological epochs. Lacking such stability, seasons might fluctuate unpredictably, impeding the endurance of intricate life forms. Furthermore, Jupiter's immense gravitational pull, as a gas giant, serves as a partial protective barrier, diverting or trapping numerous comets and asteroids that would otherwise impact Earth. While it doesn't entirely prevent impacts, an asteroid still brought about the end of the dinosaurs era. It probably lessens how often they occur. The extinction of the dinosaurs, moreover, highlights yet another unlikely development spanning more than 160 million years. Earth was dominated by dinosaurs who never developed advanced technology until a 10-kilometer-wide asteroid impact occurred. It was 66 million years ago that mammals began to diversify, ultimately leading to the emergence of primates with the capacity for abstract thought. Had that extinction event not taken place, intelligent life in its current form might never have come into existence. Consider the confluence of factors: a stable star, an appropriate galactic location, and a rocky world situated within the habitable zone. Also required are sustained plate tectonics, a substantial moon for stabilization, a giant gas planet offering protection, and a mass extinction occurring at precisely the opportune moment. While each individual condition might not be exceptionally uncommon, the necessity of all of them coexisting on a single planet during the same epoch significantly reduces the probability. The situation is less akin to rolling a single die and more comparable to rolling 10 dice, all of which must land on a 6. This understanding has been made more complex by recent exoplanet discoveries, particularly those from missions such as the Kepler Space Telescope. These findings indicate a profusion of planets with numerous ones residing in habitable zones. However, mere habitability does not ensure the development of complexity. A world completely enveloped by water, an ocean planet, could be teeming with organisms, but still lack the dry land necessary for fire and metalworking. A planet only marginally larger than Earth could retain a dense hydrogen atmosphere, thereby stifling surface ecosystems. The further we investigate, the clearer it becomes that being Earth-like is a far more stringent criterion than simply being potentially habitable. This viewpoint completely alters our understanding of the Fermi Paradox. Perhaps the galaxy's emptiness isn't due to civilizations self-destructing. Instead, it might be vacant, because hardly any planet ever perfectly fulfills all the necessary conditions. From this perspective, the silence isn't foreboding. It's a matter of statistics. Earth might reside within a confined range of possibilities, sufficiently broad for life and stable enough for complexity, and enduring enough for intelligence to arise, a pathway shaped by chance occurrences and cosmic synchronicity. And if this holds true, then we are not merely one of many voices that have fallen silent. Rather, we might be among the extremely rare few who ever managed to articulate. This notion carries both a sense of reassurance and a significant burden. It's reassuring because it dispels the looming threat of unavoidable catastrophe. The great filter would be situated in our past, within the improbable sequence of occurrences that gave rise to our planet and our biological existence. It's burdensome because it implies that the onus for consciousness throughout this galaxy might predominantly fall upon us. Should the rare Earth hypothesis hold true, the nocturnal heavens would not be quiet, for a dreadful event would have transpired. The quietness stems from complexity being an anomaly, The woods aren't teeming with concealed giants, but rather consist primarily of moss and microorganisms under countless stars. And within a single small offshoot, in a tranquil sector of the cosmos, something unlikely occurred. It began to ponder why the woodland appeared so motionless. Up to this point, the quietude has been attributed to harmless reasons. Perhaps civilizations simply fade away. Perhaps they are uncommon, or perhaps they inhabit distinct time periods. But what if this stillness is intentional? What if the galaxy's perceived emptiness isn't due to a lack of inhabitants? It's not that no one is present, but rather that everyone is concealed. This concept is referred to as the dark forest theory. This concept was most notably examined in Liu Cixin's novel The Dark Forest, though its origins lie in fictional narrative. Its underlying rationale originates from a tangible reality, game theory, which is the mathematical study of surviving amidst unpredictability. Envision the cosmos not as an urban area bustling with inhabitants, but as a nocturnal woodland where each civilization acts as a predator. Each one, traversing quietly among the foliage, is aware that other entities might exist. Each one understands that resources, energy, livable planets, and enduring existence are limited. Furthermore, each comprehends a frightening reality. One cannot ascertain the motives of another. Are these intelligent life forms peace-loving, expansionist, desperate, or perhaps more technologically advanced than ourselves? Inquiring of them is not simple. Transmissions require years, decades, or even centuries to traverse the vastness of interstellar distances. Dialogues proceed slowly, misinterpretations become lasting, and technological progress continues. A species that seems feeble currently could potentially outstrip you by tomorrow. In an environment like this forest, generating sound is perilous. If you disclose your whereabouts, you broadcast your presence to every unidentified observer within detection distance. Should even a single one of them deem you a menace or a valuable asset, their most secure course of action could be to eradicate you before you gain power. This reasoning is stark yet straightforward. Within game theory, this situation mirrors the prisoner's dilemma. If two participants lack mutual trust and the consequence of error is annihilation, the logical action transforms into preemptive action. Attack initially, remain concealed, and anticipate the direst outcome. Consequently, if all civilizations adhere to this rationale, the outcome is a cosmos where quietude signifies not emptiness, but rather survival, according to the dark forest paradigm. The cosmos remains silent, as civilizations that transmit audibly tend not to endure. Those that persist learn to keep quiet. Now consider humanity's actions for more than a century. We have been emitting radio transmissions into the cosmos. Our initial transmissions were potent and diffuse, encompassing military radar, television broadcasts, and communications reflecting off the ionosphere. During 1974, researchers purposefully dispatched a message towards a remote star cluster utilizing the Arecibo Observatory. This message contained fundamental details regarding humankind and our whereabouts. It represented a scientific overture, a form of salutation. However, within the context of the dark forest theory, this action resembled kindling a large blaze deep within a dense jungle, a place teeming with invisible predators. Some researchers contend that this apprehension is overstated, given the immense distances involved. The likelihood of encountering malevolent civilizations remains uncertain. Astrophysicist Avi Loeb has highlighted that such apprehension-driven assumptions concerning extraterrestrial psychology could merely be superimposing human worries onto unfamiliar intellects, and this critique holds merit. The thought processes of an alien species are unknown to us. Collaboration might be just as logical as hostility. A civilization that has progressed millions of years beyond us could perceive no necessity for any form of conquest. Nevertheless, the dark forest hypothesis does not necessitate widespread animosity. It merely demands the presence of a single antagonistic entity within an immense galaxy. Should even a tiny proportion of civilizations employ anticipatory tactics, the danger then becomes disproportionate. Those who make noise might vanish, while those who remain discreet could persist. And here lies the unsettling paradox. The dark forest theory does not demand malevolence from anyone. It simply necessitates prudence. Let's examine the calculations. Imagine civilization. A discovers civilization B. Civilization A cannot ascertain if B will maintain a peaceful disposition. However, A is aware that if B were to turn aggressive at a later point, preventing them might become impossible. The most secure action, from a purely survivalist standpoint, involves eliminating the ambiguity promptly, driven not by animosity or brutality, but by apprehension within such an environment. The most effective approach transforms into concealment. Highly developed civilizations would reduce their energy emissions and steer clear of conspicuous megastructures. Their operations would be hidden. They might even camouflage themselves as naturally occurring phenomena. The cosmos would appear pristine, not due to a lack of inhabitants, but because all who endured mastered the art of concealment. An even more unsettling aspect of this concept emerges. If civilizations adhere to the dark forest theory, they could deploy automated systems. These would be self-replicating probes designed to monitor and eradicate nascent technological species before they pose any danger. In this version of the narrative, the instant a nascent civilization becomes detectable, it is discreetly eliminated. This enforced silence, however, presents a philosophical dilemma. For the dark forest theory to be universally applicable, all advanced civilizations would need to converge upon the same survival strategy, allowing for no rebels or outliers. There would be no species whose curiosity outweighs their fear. On Earth, we struggle to achieve consensus among nations regarding climate policy. The notion that countless alien cultures would independently establish identical secrecy protocols appears extreme. Unless the first civilization to emerge established the rules. If one species gained a substantial technological lead early in galactic history, it might have imposed a policy via extensive surveillance systems, artificial intelligence networks, or automated enforcement mechanisms that discourage any contact, a type of cosmic prime directive. But supported by overwhelming power. Under that scenario, subsequent civilizations would develop within a regulated silence. They wouldn't even be aware of their management. The dark forest is terrifying, not due to its guarantee of hostility, but because it renders silence rational. It transforms the Fermi Paradox from a mere mystery into a strategic imperative. The absence of signals becomes anticipated behavior, and suddenly our own future decisions feel more significant. Should we continue broadcasting intentionally? Should we publicize our presence, or should we become more subdued as we grow more advanced? Already, humanity's technology is trending towards increased efficiency and directionality. Fiber optics are replacing broadcast towers. Tight beams are replacing omnidirectional signals, and encryption is replacing open transmission. We are becoming less detectable. Not by design specifically for aliens, but by design for performance. In other words, even without fear, maturity leads to quietness. If other civilizations follow this same trajectory, the galaxy may be filled with watchers, each aware of the danger posed by noise. Each meticulously scanning the darkness, none daring to speak first. Picture a forest at night. You sense the presence of others. A subtle rustling reaches your ears, and you perceive motion within the dimness. Yet no one speaks up. This quietude is not serene, rather, it's fraught with tension. The dark forest hypothesis doesn't confirm our observation. It doesn't verify the existence of hunters among the celestial bodies, but it provides a compelling rationale for the absence of overt life's luminescence in the heavens. Within a cosmos where existence is precarious and reliance is unfeasible, the most secure action is remaining unseen, and perhaps the most disturbing prospect of all is as follows. The galaxy isn't vacant, it's attentive, and we remain the sole entities generating sufficient noise to be detected. Beyond dread, beyond disaster, beyond concealed predators in the vast cosmic woods, an additional potentiality exists. A possibility less theatrical yet potentially more significant. What if the answer to the Fermi paradox isn't annihilation, nor concealment, nor scarcity? What if highly developed societies merely evolve past the point of being detectable? To grasp this concept distinctly, We must examine ourselves prior to exploring external realms. Throughout the majority of human existence, Earth remained silent. No radio transmissions exited our atmosphere. No man-made illuminations were discernible from orbit. Had an extraterrestrial stargazer surveyed our world half a millennium ago, they would have perceived woodlands, seas, clouds, and nothing further. Subsequently, something shifted. In scarcely 100 years, we grew noisy. Radio mass proliferated across land masses. Radar systems scanned the heavens, and television broadcasts disseminated universally. Our world started to emit a subtle luminescence from man-made illumination. For a fleeting period in terms of the cosmos, Earth became discoverable, not by design, but by chance. Our noisiness stemmed from our technology's inefficiency. However, observe the pattern. As technological progress occurs, it gains greater efficiency. More concentrated, more confined. Primitive radio resembled yelling across a chasm. Contemporary communication is akin to murmuring, via a fiber optic conduit. Information travels in narrow rays, signals undergo compression, and the squandering of energy diminishes. Even our orbiting devices are progressively transmitting data through precise, focused connections. Rather than indiscriminately transmitting into the cosmos, we aren't attempting to conceal ourselves from extraterrestrials. We are merely refining our processes. And refinement results in quietude. Now project that progression ahead, not for a century, but for 10 millennia. A highly developed civilization would possess every motivation to curtail energy expenditure. Extensive, luminous, large-scale constructions emitting thermal energy into the cosmos are wasteful. Wide-ranging radio emissions are similarly inefficient. Societies enduring sufficiently to advance will probably perfect self-contained systems, recirculating energy within themselves. As you become more sophisticated, signals are transmitted through confined channels, and computations are housed within dense structures. The less energy you dissipate. This could be the crucial element we've sought, as we typically look for civilizations in the same manner we seek bonfires. They are luminous, conspicuous, and extravagant. However, perhaps advanced technology resembles a sealed reactor more than a blazing fire. Instead, it's more akin to a contained nuclear reactor. Take the Kepler Space Telescope, for instance. It demonstrated the ubiquity of planets. The fundamental components necessary for life are plentiful. This finding amplified the perceived silence. If planets are widespread, why is there no evidence of advanced engineering? However, our notions of engineering are influenced by our present stage of progress. We envision Dyson spheres, enormous enclosures encircling stars. These structures would capture all their energy. We also picture vast galactic empires expanding conspicuously throughout the cosmos. We envision residual heat radiating intensely in infrared observations. Nevertheless, these are merely rudimentary, early-phase imaginings. Should a civilization genuinely comprehend physics, why would it construct something so primitive? Why would it encapsulate an entire stellar body, when one could significantly boost computational effectiveness by functioning at reduced temperatures within condensed frameworks? What would be the purpose of physically settling thousands of stellar systems if complete universes can be simulated locally for a fraction of the power expenditure? This particular perspective aligns with the transcension hypothesis, which posits that highly developed civilizations tend to progress internally. Instead of expanding externally, they focus their intelligence into systems that are smaller, more concentrated, and more effective. Rather than growing outwardly like empires, they condense, much like data. Consider the trajectory of our own technological advancement. Computers formerly occupied whole rooms, then resided on desktops, subsequently fit into pockets, and currently function on microchips tinier than a human fingernail. The trend is evident: greater processing capability with a reduced physical presence. If this progression persists for thousands of years, the most sophisticated infrastructure of a civilization could become virtually imperceptible when viewed from across interstellar space. An efficient, compact computational framework, drawing power from its star, would release only a negligible amount of surplus thermal energy. Its communications would be both encrypted and narrowly focused. Its operations would mimic natural, Astrophysical interference. From an external viewpoint, it would seem entirely unremarkable. The galaxy would seem undisturbed, not owing to its emptiness, but because intelligent life has mastered the art of integration. An additional facet of this concept is that detectability could be a fleeting stage within a civilization's developmental span. Initial technology is detectable, mid-stage technology becomes stable, and advanced technology vanishes into efficiency, implying a limited time frame, in which a civilization can be observed through techniques similar to ours. Humankind has been emitting strong radio signals for approximately a century. Perhaps that observational period extends for 300 or possibly 500 years, a mere fraction against the vastness of a 13-billion-year-old galaxy. That constitutes an instant, far too short to anticipate any overlap with numerous other civilizations, even if thousands are present. The likelihood of our detection coinciding with their noisy period could be exceedingly low. The paradox resolves itself, not due to the scarcity of life, nor because something eradicates it, but rather because we have misconstrued the true nature of advanced life forms. We've been seeking overt signals when our focus should be on nuanced indicators, and it is precisely at this juncture. Our technological capabilities are poised to revolutionize the situation. The James Webb Space Telescope is currently examining the atmospheres of remote exoplanets, seeking not merely evidence of life, but also biosignatures, chemical traces indicative of active biological processes. Forthcoming missions, such as the proposed Habitable Worlds Observatory, intend to directly capture images of Earth analog planets, orbiting proximate stars. These devices will not solely seek radio transmissions, they will also identify oxygen and methane, existing together in an unbalanced state for artificial lighting on the planet's night side and for industrial contaminants within the atmosphere. Not overt beacons, but subtle indicators. If the quiet solution holds true, then the galaxy is not teeming with glaring neon displays. Instead, it is populated by worlds that initially appear natural, yet upon more thorough examination disclose minute irregularities. A minor surplus of infrared radiation, an atypical chemical proportion, or a configuration too orderly to be coincidental. The resolution to the Fermi Paradox might not be a singular dramatic revelation. Instead, it could involve a change in viewpoint. Perhaps the cosmos is not devoid of sound. Perhaps it's a matter of discipline. Envision entering an old library where the bookshelves extend further than the eye can perceive. The atmosphere is calm, no sounds reverberate. Initially, one might assume the structure is vacant, but then a delicate detail becomes apparent. The soft whir of the environmental system, the systematic organization of volumes, the serene existence of information held throughout. The quietude was never a void, it represented structure. Should civilizations endure for sufficient periods, they might gravitate towards steadiness. Instead of grand displays, they lean towards efficiency. Rather than broad expansion, they favor subtlety. In place of clamor, they prefer quiet. This alters the emotional aspect of the paradox. The nocturnal heavens no longer resemble a burial ground. They begin to feel like an urban area, a place where all inhabitants have drawn their drapes, presenting us with one last, nearly lyrical prospect.